I had this slide up before just to show you a variety of the grades. The only thing I want to point out on this one is in the conventional steels, the limitation for the vanadium and the cobalt, which are the elements that we add primarily for wear properties and heat resistance, is limited. Most of the vanadium is down less than 2%. 1 or 2% is about all that is practical for most high-speed steels by conventional manufacturing. And in fact, when we put cobalt in them to increase their resistance to softening, we're limited to less than about 2%, usually about 1 or 1.5%, just for practical reasons. We can't get more in them and still make them hold together as reasonable tools. But with the PM process, it just gives the simple variation that we can add higher levels. You can see up to 8 or 9% vanadium instead of 1 or 2%. And even in the cobalt grades that are designed for high resistance to softening, we can also put more vanadium in those. So all it does from a user standpoint is it presents us as a steel mill with a method of making steels that have more alloy content in them. So we can widen the range of usable properties. For a user, that presents a couple of possibilities. Number one, it means you can take existing tools and look at improving their performance in a number of ways. We can make higher alloy steels. That means we can make them more wear resistant, we can make them more heat resistant, and you can look at them and say, all right, I want to go to a faster speed. I want to crank my spindles up. I want to go from 70 meters a minute to 100 meters a minute. How do I get there? And when I do that, I'm increasing heat on the tool. What can I use to keep the tool from softening when the heat goes up? Do I have a more abrasive work material that's cutting down my tool life? What can I do to increase the wear resistance of my tooling without going to a more expensive material like carbide? It also presents the option that if you have chronic failures in high-speed steel tools, if you have a lot of edge chipping, if you have excessively low tool life, you have the ability to find higher levels of those properties to address failure modes, so that if you have chipping, if you have wear, if you have deformation, you can find materials that will address those failures and make your tools a little more successful. Again, we go back to this range of steels and say, rather than look at what steel is what, we look at them, the same steels, just from a background of what properties they offer. And this is just a comparison where we've taken all those same steels and ranked them relative to each other. There's no hard number for the ranking, which are high and which are low in resistance to chipping, in resistance to wear, just in various properties that we would use in selecting a steel. So the crux of the matter is, if you use steel A, what will steel B do for you? Or if steel A doesn't work, how do you go about picking steel B that's going to be better? So my suggestion is these properties tell you everything you need to know. If you're using a tool and it's not working, and I'll say for instance M2, if you use an M2 tool, because M2 is a very, very common high-speed steel, and you find that you have chronic chipping or cracking in it, that's an issue that says breakage is inadequate toughness. So what you need to do is find the steel that you're using and the property that's the limit, and in this case you can look at all these steels and say M2 has this level of toughness, and that means anything else that has a higher level of toughness is a suitable alternative. So it says here's the world of steels that are reasonable for me to use instead of M2. And then you can look at the other properties and say, okay, in this case some of them have less wear resistance than M2. I might fix a toughness problem but create a short wear problem. So I'll go through and I'll cross out steels that aren't suitable for that. In this particular case, there are a couple of steels that aren't really high-speed steels for cutting tools in there, so I'll delete them as well. But basically, it allows you to look at nothing more than the property comparisons and find a list of grades who have better toughness than M2 without sacrificing other properties. So it leads you to alternatives. The same thing might be done if you have, let's say, M42 tools. Again, M42 is a very common material that's used for drills and end mills and high rotating speed tools. If someone speaks about a cobalt end mill, this is typically the grade they're speaking about. So let's say you have an M42 tool and you'd like to go faster and your machinery won't support carbide tooling, or you'd like to get something a little less expensive. You can look at this and say, if I go to a faster cutting speed, it's going to create a problem where the heat is going to be worse on the tool. If I cut faster, there's going to be more frictional heating. I need something better than M42 for hot hardness. What are my options there? We do the same thing. Here's M42. There's the level of hot hardness of M42. So all of these grades show the benefit that they have higher hot hardness than M42. and then we go through the same process. These are my potential grades. When I go through and compare other properties, it turns out in this case, all of these grades also have the same or better wear properties or toughness, so there aren't any property comparisons that are going to give me problems. There are going to be some other issues here. You see grindability on the tail end. Some of these grades are going to be quite high in alloy content, and they're going to be a little more difficult to machine or grind. So the fabrication issues may be a trade-off rather than the performance issues. But there's still some opportunities to get better levels of the property that limits the tool life without giving up something else. And just one other example, T15 is a material that's quite commonly used for brooches, among other applications, form tools, some tools like that. T15 is a material that is typically at about the high end of abrasion resistance for high-speed steels. It has a very high vanadium content. And if you have premature wear in T15 and you need something that's more abrasive, again, we do the same process. We find wear resistance and T15. And that's what we're looking for, is anything more wear resistant than T15. And as it turns out, there's really only one grade. There aren't a lot of grades that are more wear resistant than T15. In this case, there's really only one. This other grade up here is not actually a high-speed steel. However, it may be that in the cutting applications for T15, it's not just abrasion resistance, but perhaps it's softening too much. T15 doesn't have the highest, what we call red hardness or hot hardness. So just to create a little bit of more options here, we'll say it may be that these materials that offer higher hot hardness might be potential applications or uses in the application for T15. So again, we come up with a number of materials that offer the same kind of level of these properties and that address the limitation in hot hardness to pick for an application like that. So it boils down to a simple process of ignoring what the steel sellers have in their data sheets everywhere except in the property listings. From the standpoint of the steel mill, as I said, we look at things as chemistries. That's how we make them, so that's how we segregate them in our minds. But the users need to look at them, ignoring how we make them and what's in them, and keep in mind that you're looking for the properties. How are they going to work in the performance that you're looking for? So anytime you're looking for a different material, you start by identifying what's the starting point. What property is it that needs to be improved? And once you identify the property that needs to be improved, then you go through this process of finding a material that has a higher level of that property, making sure it doesn't give up some other critical property in between, and you come up with a listing of potential alternatives to whatever material it is that you're using. I'll point out just a couple of applications, real-life applications of that kind of decision making. In this case, we had a customer who was looking for better wear life in a cutting tool. They made just a simple little fly cutter as a test tool, a little single point tool, and just ran it in different materials to see how much crater wear and flank wear they would get on their tool. What they did in this case was to look for a material that had higher vanadium. If you remember at the top, the vanadium is really what tends to segregate more than segregate the wear properties among the high-speed steel tools. And by going to a grade that had higher vanadium than the standard material, they were able to get less wear, so they could either cut longer, cut more length of material before they came to the same wear, or they could get less wear after cutting the same amount of material. And in this particular case, again, it was just a single point test tool cutting gear materials, but just to simulate what might be happening, for instance, with hob teeth in cutting gear blanks. Another application was in looking for an alternative to carbide for cutting an aerospace titanium alloy. In this case, the cutting conditions are a little different because, of course, carbide cuts at much higher speeds than steel tools. But the change in this point was partly because the carbide tools were chipping, but partly also because in doing some work with the cutting conditions, it was possible to take a much deeper cut with the high-speed steel, because with its better toughness compared to carbide, it could take a much deeper cut in the steel and a much greater side load without breaking. And in the end, even at a slower cutting speed, the customer was able to develop a material whose material removal rate in the end was greater than that of carbide, simply because it was able to cut a much deeper path through the material that was being cut, the titanium in this material. And finally, just as an interesting side bit. We had a customer who needed to tap holes in a carbon fiber composite and was finding the fiber components were very abrasive on the standard taps, and the tap geometry was too brittle to use carbide taps. So they ended up hunting around for something that would be better than standard tap material without going to carbide, and they were able to use one of these PM manufactured materials to get enough toughness to make the tap and enough wear resistance to make the holes. So it's just an example of finding the combination of properties that are needed to make the tool hold together. As I said, we make all of our own steel, we sell our steel, we also provide services behind it. Services like this, we like to get out and talk to the customers. We do have a development lab. It's sort of fueled by feedback from our field. We probably learn a lot more from our customers than they ever hear from us. So something like this is an example of some of the things we can offer. We have service centers to provide material availability. We have developmental centers and technical support to provide that. Also, all of the technical services, the heat treat information, the data sheets about the grades are available there at our booth or online. And finally, we just want to make the point that we are here in the States as well as extremely larger in Europe. We are a French-based company. We have a much bigger presence in the European market. In the last year or so, we have made a big expansion in our sales here in the States. So the product is here and on the ground.